my presentation title is Topology Optimization using physics-informed neural network. So, and Jaewook Lee and Dongjin Kim is a co-author of this presentation. So, as you already know, the topology optimization is a mathematical and numerical method that can optimize the material distribution within a given design space. And due to the reason rapid development of additive manufacturing, the complex shape of topology optimization can be fabricated easily. So this method is being used actively for real industrial application. So I would like to talk about topology optimization for AI-based design. For this, I would like to explain the development stage of design process. So in the conventional design process, engineers need to do many things. So they need to perform the analysis using some theoretical knowledge in the textbook, and they also need to do some design using the experience. And after that, the engineers need to validate their analysis and design using the prototyping. And this kind of process need to iteratively perform to modify the design. And the second stage is a CAE-based design process. So now I think we are in this stage. So here in this stage, engineer perform only the design using the previous design and intuition, and the performance analysis is done using the CAE software. So in this case, we need to focus on the design. And the next stage will be the AI-based design process. In this stage, engineer may need to do only review the design obtained by the, maybe hopefully, the topology optimization based on the CAE software. So the topology optimization can be the core technology for this AI-based design. So next, I would like to talk about the review. I would like to review the topology optimization using artificial neural network. So recently, there are so many very active research activities to combine the ANN into the topology optimization. And I'd like to classify the previous researches based on the output. What is the output of the ANN? So this right figure is a general topology optimization procedure. So the material distribution low is determined, and then the stiffness matrix K is determined from the low distribution. Then the solution displacement field is obtained using the finite element method, and then objective function and sensitivity. The constraint function is calculated, and this process is iteratively performed. And I would like to classify the previous research based on the output. So the first category is, in the first category, the output will be the low I, and you can call that the geometry representation. In the second category, output is a Ki here. And the third category is this part, the physical variables. In the fourth category, the output of ANN will be the objective function and the sensitivities. In the final category, the output will be the final design. So in this classification, I'd like to explain more detail for each categories. So the first category is the geometry representation. So existing topology optimization assign the density field at each finite element to represent the geometry. But in this approach, the input of ANN will be the location, and the output will be the density. So when using this this approach, the advantage is like this: we can decouple the finite element method and geometry representation. So so in this case, the weight and bias of ANN will be the design variables. So we can decouple the finite element method and the geometry. So it may be possible to obtain the high resolution image with a small number of design variables. But it has a limitation that the total computational costs may depend on the finite element methods. So the computational the advantage may not that big for this case. And the second category is modeling of homogenized material properties. And for this category, so the existing topology optimization utilize some generally polynomial functions to represent the material properties. But in this approach, the input can be the structural topology of microstructure, and the output can be some elasticity tensor. So when using this approach, the advantage is like this. So because the existing topology optimization is limited in the microstructures, but using this approach, we can apply various types of microstructures for topology optimization very efficiently. But the limitation is like this. So in this case, the output number of output is very small. 9 components for isotropic material, and maybe 2 components for Young's modulus and Poisson equation for isotropic material. So we need to check the advantage of ANN compared to other modeling approaches. And the third one is a physics-informed network. So it aims to replace the finite element method. So the input of ANN will be the location, and the output will be the physical solutions in this case. So the advantage of this approach is that the FEM, finite element method, is difficult to handle. The problem is severe nonlinearity, or if there is hidden physics. But this method can handle this kind of problem by combining with the PDE, combining the PDE with the experimental data. But there will be no clear advantage in linear simple problem. It is not that computationally efficient. And the fourth category is modeling of objective or sensitivity function. So we utilize the adjoint variable approach for sensitivity analysis, but in this proposed approach, the sensitivity will be the output of ANN, and the density distribution will be the input. And the advantage is like this. So the adjoint method is very complex, mathematically complex. If specifically, if the objective function is very difficult one, not just simple one. So in this case, that we can utilize the auto differentiation for the sensitivity analysis, but there will not be a clear advantage for the problem with simple objective function. So if the objective function become very complex and not well defined, this approach will be very meaningful. Okay. And the final one is final design generation. Okay. So for this category, we have 3 different one, and the most of previous research are actually in this category. So the first one is the optimization iteration reduction. So in this case, the intermediate density at the intermediate iteration will be the input, and the final design result will be the output. So we can get the final design from the intermediate iteration result. And the second one is a resolution enhancement, and the Professor Zhang present this kind of approach. So in this approach, from the low resolution image, we can obtain the high resolution image. And the third one is a one-shot design. And in this category, the input will be just a design domain setting. So the design domain, loading, and boundary condition will be the input, and the final design will be the output. So this all three categories. In all three categories, the output is the final design result. So the advantage of this category is like this. Conventional topology optimization required at least 50 iterations, but using this ANN, we can obtain the final design very fast. But the limitations is like this. We require large amount of data, and if design domain will be changes, this approach may not work well, and the unconnected parts appears frequently, so need to check physical performance of final result. These are limitations. So this is the end of kind of literature review, and I'd like to talk about our study for the geometry representation, the first category, and the physics-informed neural network, the third category. So as I already explained, in the geometry representation, the input of ANN will be the location, and the output will be the density. And the design variable is weight and bias of ANN instead of element or nodal density values. So we try to utilize this kind of approach, and this is for this simple geometry. So using the ANN, we try to represent this kind of simple geometry and investigate the effect of hidden layer activation functions. So after the investigation, we can find out that the side and hidden layer function works well for this kind of problem. And we also investigate the effect of a number of hidden layers and units. And if the number of hidden layers and units are large, this approach does not work well. So we can conclude that we need to find appropriate model parameters, model hyperparameters, and activation functions. And this is modeling this is target geometry for more complex target geometry case, and with some unstructured position case. This is a position for position of ANN input. So in this case, also the side and activation function works well for this kind of geometry representation. After that, we try to apply topology optimization using geometry representation. So here the design variables are weight and bias of ANN. So the low will be the neural network, and this is Young's modulus. And we utilize some unconstrained optimizer. So to consider the volume constraint, the augmented Lagrangian approach is applied. So this is a topology optimization result. Result is not that good. So this is for the design result for the cantilever beam problem. So anyway, the topology optimization using geometry representation works like this. But the problem is that this approach cannot catch the symmetry geometry. This is TOUNN, the previous works by Professor Suresh. So if you see this kind of result open to the public, so to obtain this symmetry result, some additional conditions, symmetry condition need to be applied. Without this symmetry condition, the result is is not that good. Similar result, the unsymmetry, and it is diverse finally. So this kind of phenomenon happen when you use it when you're using the geometry representation for topology optimization. Okay, the final topic is physics-informed neural network or topology optimization. So what happens if we use neural network instead of a finite element method? So the physics-informed neural network is a kind of numerical method for solving partial differential equations. And here, the ANN neural network are used to approximate a solution, physical field, instead of a piecewise polynomial function in FEM. In FEM, we utilize the piecewise polynomial function to approximate the solution, but here it will be replaced with a neural network. And since the first work in 2018, this work will be the first work 2018. The vigorous research have been conducted for solid, fluid, and electromagnetics. So many works have been performed in this field. And based on the literature, we need to think about why do we need to use the ANN model for the governing to solve the PDEs. So this is a figure for data physics scenarios. If we have a big data, we can use just a data-driven model, and this model may fit well, but the prediction may not physically inconsistent. And if, for this case, if the physics is well known and well defined, and then we can use the conventional CAE method, conventional numerical method, that finite element method. But for the problems such as turbulence, viscoelastoplastic material, such problems, physics is partially known, and we can have some measurement experimental data. And for this case, we can combine the partial differential equation together with the boundary condition also together with the data, and this will be sum of this whole part will be the loss function, and then we can find some hidden physical problem or some parameters or something like that. Okay, that is why this is the answer why we need to use the PINN or to solve the PDE. So this is a comparison between the finite element method and the PINNs. So the unknown variables of finite element method is nodal state variable. It has a physical meaning itself, right? So nodal physical variable will be the unknown variables, but the PINN, the weights and biases of the neural network will be the unknown variables. And in FEM, we can use the direct solver for linear problem and the iterative solver for the linear problem. But PINN should utilize the iterative solver always, so it is not that efficient maybe. But the FEM need to mandatorily define, and we need to know the governing equations, material properties, and boundary condition, and the material distribution. But for the PINN, it is optional. It's okay if we don't know the material property, for example, but we need to add some data instead of that. So when the data are given, the PINN can approximate the solution of PDE if some of required information is missing. So this is various formulations for PDE, the PINN. So we can apply the strong form loss function, directly apply the PDE, or the weak form, the energy functional, or some functional form, weak form. And the solution form, for the solution form, we can apply the simple displacement form. This is for the solid mechanics problem. And also we can apply the mixed form, displacement and stress as some variables. But for the mixed form, we need to add some additional the loss function like this. This is a relation between the stress and displacement. This is for the zero stress condition. So many loss function for this case. And for the boundary condition, we can softly enforce the boundary condition using the additional loss function, or we can hardly enforce by setting the solution field itself. In this case, the solution field automatically hardly satisfy the boundary condition. So in the cantilever beam problem, we check the effect of the PINN formulations. So we compare the strong form and weak form solution together with the FEM. So as we already expected, the strong form is not that good. So weak form may be much better, even for this case. And this is the effect of displacement form and mixed form. So the mixed form, as I already explained, need very many number of additional loss functions. So both cases give some reasonable solution, but the displacement form may be enough. So as you can see, the displacement and normal stress may be good, but the shear stress is not that good so far. So we need to study more about this. So this is the conclusion of the study. So the weak form and displacement form with hard enforcing boundary condition may be okay. And using this, we try to apply the topology optimization using the PINN. So this is the region 2 studies in the archive. The recently 2 literatures are publicated in archive. And we try to apply PINN for topology optimization. In this previous approach, the geometry representation and PINNs are combined together. So we also try to apply both the geometry representation and PINN. And this is the result. Result is not good. So in this case, the design variables is weight over ANN. So that is maybe the reason. So if we see this previous research, they update these 2 updates. So they update the density first, and after that, using the density, they update the weight of the ANN. So maybe if we do this 2 steps simultaneously, the result may not be good. So we are trying to study more about this approach. So this is the end of my presentation. So any questions?
Okay, can I ask a question?
Yes, please.
Yeah, hi. So it's interesting to see somebody actually using PINN and connect with structure design. I just have a question on so when you train the PINN for these problems, so how long is the training time?
So this is in this case, loss function is energy functional, like a finite element method. So just 200 or 100, 200 the iteration might be enough, but okay. I remember maybe 1,000, more than 1,000 for solving some problem. So it is not that efficient. So PINN itself requires many number of iterations. Yeah.
Yeah. That's the sort of like trade-off, right? So you don't need a lot of training data, but then as a consequence, the training time is increased because it's more difficult to train, right?
Yes, correct.
I see.
But it may have an advantage if the physics is very difficult. So for the linear problem, the advantage is not that clear, but if the problem, nonlinear problem, for very highly nonlinear problem, maybe okay. I hope. But,
I see.
Yes. Thank you.
I see. Okay. Thank you very much.
Yeah. You, Professor. Yeah.
Thank you for your nice presentation, and I have learned a lot. And
You're
so,
very nice.
yeah. So I'm curious about the future of this research area. So do you expect sometime industry can utilize these methods?
Yeah, I hope so. I do hope so. So we have to, make the method more efficient, so they will be interesting to use, right?
Yes, and for very difficult problem, maybe for complex, like a crash or the kind of problem, the highly nonlinear problem, yeah, this can be interesting work because the existing one is very difficult to learn and understand. And
Yeah, my personal view is we somehow cannot fully rely on neural network alone, and we need some physics involving it. So maybe combination of a neural network with the traditional method like TO method would be a good choice.
Okay, yeah, yes, thank you for your comment.